Excellent. Thanks for the introduction. And I think leading on quite nicely from the previous talk, I'm going to talk about the work we've been doing of integrating physical and digital design methods into design for fabrication. So this project was led by Chris Weichel and John Hardy, neither of whom could unfortunately be here. So my name's Jason Alexander, and it's also a collaboration with Hans Gellersen. And all of us are at Lancaster University. So if you're already bored of my talk and want to leave, here is the key take-home message. So ReForm provides a more flexible design process by combining physical and digital modeling. What this allows us to do is to take advantage of the benefits of physical modeling, modeling in the real world, and the benefits of digital modeling within the same process. So just so you can get an idea of the ReForm system and the work we've done, here's a short introduction video.
New way to think about digital fabrication. ReForm blends physical shaping with digital design through a new bidirectional fabrication process. We can take advantage of things that hands are good at and use the machine to perform operations that machines are good at. Taking this approach opens up novel design interactions. This allows the design environment to stay in the physical world, whilst all the while your changes and modifications are kept track of in the digital model. This allows for low-cost iteration, quick adjustments, and the ability to undo and redo the actions as you design. We use head tracking to overlay the digital scan on top of your physical model. This can also be used to preview and select digital operations live. You can export your model at any point and share it online, or produce it via a conventional 3D printer.
Okay, so that's the ReForm system kind of in brief. And so for the rest of this talk, I'm going to talk about two things in particular. The first is the concept of bidirectional fabrication. So this is how we entangle digital modeling and physical modeling to change the way we do design. And the second is the the bidirectional fabrication implementation. And this is what's the machine which is shown on right, and it was featured in the video. So just taking a step back to start with, we wanted to think about why on earth this was a good thing to do. And so as we found in the previous talk, the creation process is unidirectional. So once an object has been fabricated, it's completely disconnected from its virtual model, which is in a computer, in a PC. So what are the implications of this? Well, this ties users into using virtual modeling tools to do all of their design. The virtual design must be completed before it's fabricated, although now we have some other solutions which might make this not a problem. And quite importantly, any reshaping you do of the physical object no longer influences the virtual object. So if you take the physical object and you file away at little bits, or you drill extra holes or add extra bits on, that is not reflected in the virtual model. And so those changes have to be reflected in the virtual model before you can reproduce the object accurately. So to overcome some of these problems, we thought about bidirectional fabrication, and this is the way it works. So I'm glad to see that people have also used cups as previous examples. Clearly it's a good one. So assume the user starts with a virtual model of a cup. And then they think, well, actually that handle, that's not very useful, so I'm going to get rid of it. So they delete the handle from the virtual model. In the bidirectional fabrication situation, the physical object is immediately updated to reflect this change. So the handle is removed. If then when the user is trying it in the real world, they realize that actually that handle was really important, and so they sculpt it and put it back on, then in this process, the virtual model is immediately updated as well. So both the virtual model and the physical object are always in sync. What this means is that users can flexibly move between these two different ways of design. When digital modeling is preferable, then they can use standard digital tools. But when it's preferable to change things in the physical environment, they can use the hands and tools we have in the physical environment. So here's some benefits of thinking about fabrication in this way. So the first is that we can use the right tool for the right job. So expressive, creative, and artistic manipulations are typically better performed in the physical world. We can use our hands to model things, we can use tools that we have lying around in order to create the shapes and patterns that we may want to fabricate. But precise and repetitive actions are often better performed using digital tools. So if we want to drill holes to a certain depth, or we want to cut edges at very precise lengths, then we're far better using digital tools to model that and then to have that reproduced. It also means that we can do something called evolutionary fabrication. So that in the bidirectional fabrication process, we can make incremental additions, subtractions, or updates onto the object. So this means that we can try on the fly. So we can validate that any small change we make to, say, a virtual model is correct in the physical real world. So we can check that the style, the size, still work in the correct way, and it is still fit for purpose. And when it is, we can move on to designing the next step. And finally, what this allows us to do is to also have physical version tracking. So the physical model is continually synchronized into the digital model. And this allows us to do things like physical undo, physical redo, and to go back to a previous version, anything that is stored away in the digital model. So if you drop your physical model onto the floor, you stand on it, you smash it, and it's all in pieces, you can just scoop all those pieces up, stick them back into the machine, and hit undo, and it will return to its previous physical state. Okay. So in order to validate the bidirectional fabrication process, we built this machine that you can see on the right here. And so this is an additive and subtractive fabrication system, and it uses a reusable polymer clay. So once you're finished with your modeling with this clay, all you need to do is to put it into a ball and stick it back into the machine, and it will reuse it next time it does some extrusion. So this clay can be reused and reused and reused. So the clay is extrudable and sculptable when it's warm, and it's machinable when it's cool. Okay. So in order to make this happen, this system implements a variety of capabilities, which then mean we have several operations. So the first that I just mentioned is additive and subtractive fabrication. So the machine chooses which fabrication method is best, depending on what needs to be created. Sometimes it uses a combination of both in order to produce the desired result. It includes high-resolution 3D scanning and a rotatable turntable. So by placing a physical object on the turntable, it'll move it around and scan it from all sides. This is then reflected in the digital model. And it also contains an augmented reality user interface. So what this does is it overlays digital information on top of the physical object which is sitting inside the machine. So this means you can configure things like areas you want to flatten, you can preview changes which the tools are going to perform. So these capabilities enable a series of operations, which I'm going to talk about in a bit more detail. So it allows us to synchronize digital and physical models, and it also allows users to do physical shaping and digital modeling, and it provides this history and versioning system that I mentioned earlier. So to start a session, what we have is either a digital model or a physical object, and the user can choose. If we're starting with a digital model, then it may come from one of these places. So it may come from an online repository, such as Thingiverse. It may be a pre-existing CAD model, or it may be a previously saved ReForm session. Once we have which one we've chosen, the one we're after, the system will then fabricate the object so that we have a digital model and the fabricated physical object. If we, however, want to start with a physical object, we have a couple of choices. We can start with an object in the real world. So this might be your favorite mug, it might be half a broken component, it could be anything that you want to have reproduced. Or it could be a clay model that you've already started working on. If it is an immutable object from the real world, then the machine will scan it, and then it will first print that out in clay, so that you can then go away and mold it. So whichever path we take, we have a physical object and a digital model that are both in sync. So then we can perform some of these operations. So obviously we can mold this clay with our hands, Or what we found quite useful as well is to use typical tools that are used in clay modeling, so knives and scalpels and these kind of things. And also, quite interestingly, is that we can use other objects in the real world. So if we're designing that phone holder, then we can physically place the phone into the clay to make a mark to channel out a channel for it to sit. We can also perform a range of digital operations. And so the first type are global operations. So if we want to perform something on the physical object as a whole, then we can do things like we can flatten an edge, and we can use the augmented reality overlay to specify that. Or we can scale an object. So if the object is too small or too large, we can ask the machine to increase or decrease its size. We can also do selective operations. So the machine will recognize when you've annotated using a standard Sharpie on pieces of clay. And so this may happen, or this may occur so that you want to extrude a patch or intrude a patch. You may want to produce accurate holes. Or, to me, most interestingly, is you may want to repeat a pattern. So if you have put a lot of work into designing a very small specific piece of the object and you want that to be repeated, you can just color it in and instruct the machine, and it will go away and reproduce this across your whole physical design. So here's one example where a user annotates a game controller for a channel that they want drilled out. So it's annotated, scanned, and then the system goes around and channels out that material. So of course, users can also perform digital modeling in any of their standard tools. So any standard CAD tools they can use to change the digital model. We also have this history and versioning feature, which is particularly useful when you're going through an iterative design process. So we can make changes to a physical object, so maybe we want to cut off the corners, and if we're unhappy, we can rewind to any previous position in the design process and return to that state. So this is really handy when you want to quickly try out different designs or when you're working with multiple people. And so here's an example of someone who's modeling a game controller and accidentally smudges one of the buttons. So we put it back into the machine, it'll scan it, and we instruct it to return to a previous state. So in this case, it used both subtractive and additive fabrication in order to reproduce the object in its previous state, to do this physical undo. So I'm not going to go through the implementation in too much detail, largely just to say that we integrate a variety of reasonably well-known components. So we have additive and subtractive fabrication. In this case, we use a clay polymer, which allows it to be both milled and to be modeled in the hand. We have a jog wheel for simple user interaction, and a depth sensor at the top there, which can track the user's head to correctly overlay the augmented reality preview. So we have a variety of different example outputs that we've had from the machine. These include things like embedding electronics into a new device prototype, designing a game controller, or using things like a mobile phone as the starting point for various designs. And I was pleased to see this came up in the previous talk as well. But probably more interesting than the output which comes from the machine is to think about how this actually changes the design process. So there's a really interesting question about how does this change the way that we create things? Does it result in better objects being designed, different objects being designed, or them taking longer or shorter time? So I don't actually have the answers to these questions, but I'd love to hear from anyone who thinks they know or thinks they could tell me how we should measure that. How do we measure the way that design is done differently using traditional processes and using a machine like ReForm? We also have this interesting trade-off between accuracy and time. So ReForm is able to produce fabricated products at different resolutions. Sometimes a quick and dirty prototype is sufficient. Other times you need a highly accurate one. So we're looking into ways that the user can configure the fidelity of the prototype produced. Okay, just to sum up, we've introduced the concept of bidirectional fabrication, which means the digital and physical worlds are brought closer together. So the models in both are always kept in sync. And we've provided an example implementation of this, which has allowed us to demonstrate changes in making it into the design process, which makes it far more flexible. That's it. I'm happy to take any questions. Stunned silence. Awesome.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I'm curious what things people made with this besides game controllers. Like what kind of creative things did they come up with?
Yeah, so we had a few things. So I think the most interesting stuff for us was when we tried to embed electronic components into this, because the great thing about that is, you saw one example with a screen. You can poke the screen in and you can immediately have an outline of the size, and then you can rearrange buttons and things around it. And so to me that was one of the more interesting use cases, because this is what we do a lot, is try to design casings for electronic components. So I think one of the big advantages was when you could take physical objects from the real world and mold the clay around them. So we had examples like that. We had cups and we had pen holders and various things like that, which often included these physical objects.
Thank you.
Any other questions from the audience?
Hi there, Cesar Torres from UC Berkeley. Really fascinating talk, really excited about this area. I was wondering, in your example, you kind of showed how a user would mark something and then the computer would refine it. And while this makes the whole process much more simpler and easier for a user to create these professional-looking artifacts, it does take away a little bit of this craft, right? This craftsmanship, this expert behavior that you see in these cultures. So I'm wondering if you envision your system in a kind of more professional master-apprentice type situation, and what it would do in those types of situations.
Yeah, really good point. And I guess the thing to note is that we don't stop people from doing these crafty expression things themselves. And so the machine is just there. If you require assistance to do things accurately, then that's mainly what it's designed for. And I think what would be really interesting is to see how sort of really professional craftspeople would take to this machine. So one of the complaints they have is that 3D printing is all done virtually, it's all kind of very crisp and sharp, and then you have to print something out. And so I'd love to get some professional kind of creative people in to see their opinions on it. Yeah, it's a really nice point.
So basically you're using the combination of physical and digital world to like design 3D objects, right? But I don't know whether you're aware of, there was a paper several years ago from MIT Media Lab, 3D, which is actually a milling machine, but that kind of have the digital model as information, and it gives you formal feedback when you're like milling a 3D object. So I think in that case what happens is that the physical object is being augmented with digital capabilities because it gives you feedback in real time. But at the same time it gives you that craft that according to the previous one, that like it gives you that creative freedom to get the feedback from digital information, but at the same time have that creative freedom for expression.
Yeah. Thanks.
Okay, let's thank our speaker once again, and